wordt. I can, let me share my screen. Here we go. And let me also hide these controls. So, okay. So I would like to say something on behalf of the group in Amsterdam. I will not talk about the whole group in Amsterdam because we have a lot of people here, both at university and at NikHef. But I'll specifically talk about Juan and myself because we were involved in the staff exchange proposal. So you can see my group here with 2 postdocs, Ankita and Johannes, and 1 PhD student, Max. And Juan's group is currently 1 postdoc and 2 PhDs. And I'll talk about a little bit of my expertise first, and then a little bit about what Juan is working on. So I'm interested in actually describing jet cross-sections and jet substructure, which is like the internal structure of jets, both to study the standard model better, but also to search for new physics. And an example of this would be resummation for Higgs production with a jet veto. And so this is the case where you produce a Higgs, you say there's not allowed to be any extra jets, or maybe you say you have 1 jet, but not 2 jets. And the fact that you have, on the one hand, the Higgs mass, on the other hand, is jet veto, which have very different scales, allows you or requires you to do some resummation to get good predictions. Another thing that I'm interested in is prediction or proposals for new observables. I think here the example that is, well, depends a bit on your community, but the example that is most known of this is n-jettiness because it's been applied in many different contexts, both in jet substructure or as a slicing variable. Something that I've been working on with Ignacio is looking at this transfer momentum with jets. And there was a specific choice of jet axis that was really important to get it to work. And to do all these things, I apply and develop factorization and resummation in soft linear effective theory. And Ignacio already gave a nice overview, so I'm very happy to not have to do that as well. And they're also, like, when it comes to developing new things, so not just applying them, some of the things that I've developed in my career, for example, the beam functions or track functions, which describe if you do a measurement on charged particles only, then you need some kind of new non-observed object. And this is it looks a little bit like a fragmentation function, but it's a bit different. Or sket plus, which is used to do resummation of more than 1 variable. So sometimes you have more types of logarithms in your calculation that need to be addressed. So I want to just show you a couple of examples of some recent work, and recent I really mean like basically the past half year. So this is something that I finished at the end of the summer. This was with Frank Tackman and some other people in our groups. And this is a prediction for Higgs plus 1 jet production. And so that really means 1 jet, but not more. So there's a restriction on additional jets. And you can see that also in this figure where it says PT cut is 30 GeV. So there's no jets above 30 GeV allowed, in addition to the 1 jet that you found. And basically the gray band is what you could already do before with the next leading order calculation. Adding in our resummation, you get the red prediction. And so you can see that, particularly if you go to larger values of the Higgs PT, this reduces the uncertainty by up to like a factor of 2, or maybe even a little bit more. So to kind of just put in the concept of what had been done before, we added an extra n for this resummation. So before it was NLL. And we also worried about the non-global logarithms of the jet radius, and we addressed these things. So this is one example of something that I've done. Another thing that I want to mention is energy correlators. And this is a topic that has really got a lot of attention recently because energy correlators provide a natural way of separating physics at different scales. And so many of these applications, whether it's like in the quark-gluon plasma or extracting top quark mass, they basically say, well, it's just like this, the spectrum of the CMB. You can see different structures appearing, and they can directly be interpreted as physics at that scale. And so one of the things that's nice from the theory side is that the calculation, the theoretical description is simpler, which makes it also more interpretable. And so the application that is being used for, I mean, I should say that the phase we're in right now is a phase where lots of theorists have proposed things, experimenters are picking up on these things. So it certainly has a lot of experimental interest, but I would say many of the things that have been proposed have not really been shown yet that they really work as well as we maybe hope they do. But one example that does is the extraction of the strong coupling. So this is the most precise measurement of the strong coupling from jet substructure. Not the best, of course, you can do worldwide, but for measurements on the structure of jets, this is really the best that's currently available. Another example is a measurement of the top quark mass, where in the standard approach, you either have a very precise experimental measurement, but in some kind of Monte Carlo scheme that you don't really know, cannot really translate back to like a top quark mass in your Lagrangian. So, well, you have some precise number, but you don't really know what it means theoretically. Or you have some kind of measurement that is not so precise, but theoretically very well in control. And they kind of, it looks like energy correlators can break that kind of trade-off and actually do something that's both theoretically under control and precise. And also in the context of the quark gluon plasma, this is something that's really interesting. So I want to highlight two things here. So in one project, we looked at generalizations of, or like a new parameterization of higher point correlators. Because basically, if you try to calculate an n-point correlator on m particles, well, you end up with something that scales like order m to the power n. And we actually found that depending on what you want to exactly measure, you can parameterize things in a bit different way and cut this order m to the n to order m squared, roughly speaking. And so this is something that's actually very interesting, at least for experimentalists, because they calculate this on jets, say, with maybe 30 particles. And then if you do 30 to the power 3 or 4, it quickly becomes rather time-consuming. But our new way of parameterizing things also gave very nice visualizations. And I should probably compare like a visualization with the old parameterization where you see that it looks rather different, because you get kind of a slice of this. But with this new visualization, you can even see difference between different jet samples just by eye here. So on the left, this is a jet, a QCD jet, and on the right is a W boson jet. And you can see that there's kind of like this C-shape ring on the outside that is really coming from the W boson mass. So something else that we've done with energy correlators is do predictions. And this is some work that's not quite finished, but here's already like a preliminary comparison with data that was presented at hard probes. And so you can see the experimental data, which, I mean, we just saw in the previous talk also energy correlators in E plus E minus, and you will see that the bins are much, much finer than there. And the reason why that is possible is because this is done on tracks. So this is done on charged particles, and the way that these are measured experimentally is quite different than for the neutral particles, which is why I get this really amazing angular resolution. And so we compared the prediction or the measurement to our predictions, where we treat the fact that you do this measurement on tracks using something called track functions. So it's some kind of non-perturbative object. And well, we can see that we describe both the back-to-back region, which is described by some kind of TMD resummation, like Ignacio talked about, but also a linear region, which is described by a very different type of resummation. Okay. So another example that I want to mention is as related to transfer momentum, but this is using QT slicing to multiple jets. And so what is the problem? If you want to do higher order calculations, you have to cancel infrared divergence between the virtual and the real part of the calculation. And one way of doing that is by slicing. And so what you do is you say, I'm going to measure some or I'm going to calculate some cross section, and I have some resolution variable. So take the example of Drell-Yan, where you produce like a photon or a Z boson. You can say, let's take the QT of that photon or Z boson, and if it's below some threshold delta, that part I will treat separately from the region above. And the region above delta, I know this photon or Z boson recoils against QCD radiation, and so it effectively reduces to a calculation that involves one less order. So you really get to like, instead of an NNLO, you now have an NLO calculation, but you have one additional particle. And in the first part of the calculation, this region where QT is between 0 and delta, there you can actually use factorization formulas to describe this. And so QT slicing there's more ways of slicing things, but QT has a great track record, except that is restricted to very limited processes. In particular, you cannot really do it for jets, because you can have situations where you have a jet and you have emissions inside a jet, but you still have QT is 0. And so here I use an idea that we also developed with Ignacio of applying this winner-take-all axis. And interestingly, we can then use QT again as a slicing parameter. And so a proof of concept you can see here in this figure, where basically, you can maybe ignore it. Well, what you can see is that we have these two terms in this equation that correspond to the two colors in the plot. And then the sum is the real answer. And so you could also see kind of the challenge you have numerically in doing this, because you have two relatively big pieces that should cancel each other to get you the final results. But in the lower panel, you can see more clearly what the total result is. And so as you go to a smaller value of this delta, which is to the left of this plot, you can see that the blue dots are converging to the known result in this case. And so this is just at next leading order, but most of the ingredients are also available for doing this at one order higher. Okay, so I'm going to switch to the things that Juan has been working on. And basically he's done a lot of machine learning, but is specifically in two specific contexts, namely a global analysis of data to constrain the standard model effective theory, including also matching to UV complete models, but also to study the proton structure, and specifically to use a neural net to parameterize the partition distribution function that also Ignacio talked about. A more recent interest of him is in neutrino physics. So the neutrinos are being produced in a very forward region and are measured by, for example, phasor and how they constrain proton structure. But he also has a general interest in machine learning and AI methods for particle physics applications, which I think connects very well to the overall goal that we have for HeI, or I don't know how we pronounce the acronym. So why SMEFT? I mean, SMEFT gives you a model-independent way of describing new physics without picking your specific one. So you get a complete basis and a systematic parameterization of BSM effects. It's also a full-fledged quantum field theory, so you can calculate higher orders in QCD and electroweak. And yeah, then you can say, rather than constraining some specific model, I can now constrain the parameters of this theory. I can compare that then to the data, and then with the constraints on these parameters, you can also then compare to specific BSM models. And so this is something that he's been working on, and yeah, it gives you a general way of like trying to constrain new physics at the LHC. And it allows you to combine also different experiments. So here, specifically the HeI-PT from Atlas and CMS and the flavor physics from LHCb. And in this approach, again, just as in the proton structure, he uses machine learning to optimize this. So the other example I already mentioned it now twice is proton structure. This is a topic he's already been working on for a long time, and he's a member of the NNPDF collaboration. And so the question is like, how do you describe the structure of a proton? Well, on one hand, we learn that the proton is an up and a down quark. On the other hand, we also know it's a much more complicated story. And yeah, he has developed this, or he's been at the start of this NNPDF collaboration, and this is something he's been working on a lot. And a recent highlight I included here is from a Nature paper for the evidence of intrinsic charm in the proton. And so as I mentioned, a recent interest he has is in neutrinos at the LHC, where these are neutrinos that, well, you can see the process here on the top left, where you can see a D meson being produced in just the scattering at the LHC, but this D meson then decays to a neutrino, and that neutrino is measured much further down. And so you can then see the neutrino there. And yeah, well, the first detection was in March 2023 from phasor. And the interesting thing is that it gives you constraints on the structure of the proton. And well, there's different plots to kind of illustrate that. So these are for different PDFs. And you can see the baseline in the top panels in red. And then what happens if you include a future physics facility, forward physics facility, and maybe in the bottom panels, maybe clearer to see, then you can see that for the gluon PDF, if you want to probe the small X region, you get a much stronger constraint from such forward physics detections. And so if you think about like how does what we do fit into HeI, there is, from my side, I'm interested in exploring QCD aspects, both in the concept of LHC, also the EIC physics. I mean, there's a natural connection with the work package 2, which we were involved in writing on factorization and quantum entanglement. But I also thought, given like the expertise that is here, like it could also be interesting to explore connection to more formal developments through energy correlators. And from Juan's side, I think he's very interested in new machine learning and AI tools that are relevant for LHC pheno and hadronic physics, where again, there could be connections with different parts of this proposal. So, okay, that was it. Thank you.
Thanks, Wouter. Are there any questions for Wouter? Maybe I have one question just to clarify to myself. So you mentioned that you were computing n particle correlators, is that correct?
Yes.
But at 3-level perturbation theory, what did you mean exactly?
Oh, good. So there were two very different points here. So the point of this slide was not about calculating them in perturbation theory, anything like that. It was actually about like, suppose I give you the four momenta of, say, 30 particles. Calculate for those 30 particles the endpoint correlator. And if you would do the brute force, you end up with order m to the n.
I see.
But it turns out that, I mean, in the end, you're not interested in all correlations. So for example, what people had defined before was looking at a projected correlator. You say, well, let's look at the largest distance between all these different particles in some sense to project down to some single or two variables. But that would still be as computationally as intensive as just doing all possible correlators. And we found a way of parameterizing this that cuts it down like to order m squared.
I see.
So it's really like at the level of like defining your observable in a way that's useful experimentally. And we actually found it doesn't really change much on the theory side. So the calculations that existed are only minimally affected. Yeah.
I see.
Like I think in the collinear limits, so in the small angle limit of the energy correlator, the first change is at next to leading log accuracy. Yeah, because it was never an issue for the theorists, because the theorists always calculate with only a few particles, right? You do up to some order of perturbation theory, you have a very limited number of particles, so that this was never an issue for them, but it was really an issue of like, how do you define something that's useful for experimentalists? But I think for me, at least for me, it also suggested that there's space, especially if you think about higher point correlators, there's space to think about what are the useful things to look at. I mean, it's not really mapped out yet. Like, what is the best way of doing this? Yeah. This was a real calculation. So this was a calculation that we did, but this is a 2-point correlator in E plus E minus. Yeah.
I see, thanks. There any other questions? Maybe I have another question related to what you mentioned about Juan. I'm not sure maybe he's not online.
He's not online right now. No, he apologizes.
Ignazio before mentioned something about lattice computation for PDF. Is that the same argument? Same? Is the two the comment that you made about Juan that is using neural network to improve on PDF? Is this related to?
No, it's not related to lattice.
No, it is for him. It's for fitting, which also does connect to something that Ignazio mentioned, which he said like this has been used in a collinear context. Well, that's exactly the thing that Juan has been doing. So he has been using a neural net to parameterize the PDF, but it's really about like the data, fitting them to data and improving the theory side, but not from like first principles using lattice. No.
Yeah, I imagine that maybe it was I know that there are some. I was
Sorry, the connection.
so what would
Oh, sorry, go ahead.
What would be in the energy correlators something useful to have under control from the theory point of view that is also useful experimentally? Do you have a take on that?
There's many things I think that are useful from the theory point of view that would be also interesting experimentally. I mean, I think yeah. I would say, like, for example, so this example that I mentioned for the top quark determination, much of these studies have now been done at the level of Monte Carlo simulations. And there is some theory understanding there, but it's not that there is actually a theoretical prediction yet that one can actually use. And so I think these energy correlators, they would depend on both the type of jet that you're looking at, as well as like this specific correlator you're going to look at, whether it's like some 2-point or 3-point or higher point correlator. And I would say that, there are much of the things are at the level of that there's some calculations, for example, the 2-point correlator, but there's also many things that rely on some Monte Carlo simulation, which are interesting for getting an idea, but I would not say are very precise, or at least not very precise yet. And so having a better understanding of that, or having predictions just there would be already very useful. I mean, another topic aside from perturbative predictions is also how do non-perturbative effects show up there. I mean, some of that is related to like how do non-perturbative effects show up in TMDs, but there's also other aspects to it.
I see. Thanks.
Sure. Yeah, I mean, I think we're also kind of in a stage where there's many papers being written that are kind of motivational. And then the hope is, of course, that experimentalists pick them up. And I think there's also a lot of interest on the experimental side with things being measured. But of course, at some point, it also means that then theory has to move again to produce like more precise predictions, or predictions at all that are based on theory rather than on only a simulation. Yeah.
See, I see. Are there other questions or comments from the?
I don't know if Alexei has some questions. So Alejandro,
Maybe Alexei, do you have questions?
Alejandro, question. So we had a seminar of Brown, Vladimir, this morning about conformal stuff. So do people doing conformal field theory have some hint, something that I don't know, raised thoughts or of possible things to do, or even questions on how this stuff are applied in their usual life and in QCP, things like this? I don't know, probably they ask.
No, I don't know. I mentioned to Alexei the other day. So just from theory point of view, it looks like that unless you fit the PDF, there can be anything, right? So, but that's of course they're theory dependent, but so sometimes it's useful to ask the question whether you can bound the quantity that you're studying. It's a non-perturbative, but that doesn't mean that you cannot find some bounds on it. So maybe that was and this bound maybe may be used to project out the bad data when you fit. I don't know. That was something a question I asked.
Oh, but concerning jets, it's not clear how to apply conformal field theory because jets violate Lorentz invariance by definition. You introduce some particular axis or some particular angle.
Right. After you integrate, I think it should be, you might restore.
If you integrate out all jets, you should restore. But I believe that Wouter is exactly interested in not integrating out jets.
I see. Yeah, okay. I don't know.
No, but there is a thing like Vladimir made the example of big physics. In big physics, there are masses, but some masses are so high that then they become irrelevant in the sense that they become at a high scale, and below that scale, you don't have masses anymore. So there you can still have a conformal symmetries. And for jets is not really the same. We have the momentum of the jets, which is the high scale. But then when you go to jet structure, then this momentum is a kind of high cutoff that does not intervene in the low energy dynamics.
With substructure of the jets, I don't know, but I remember I heard a talk by Lorenzo Magnier, who say that if you consider this energy correlation and on a large size sphere, far away from the collision, then somehow the structure that you get is similar to the two-dimensional conformal field theory. I don't really remember details, but there was something kind of interesting. Yeah, so yeah, you can ask him to give a talk. He has some.
You can ask him to give a talk. I mean, there are Torino people. I think they see Lorenzo.
Yeah, there are some Torino people. So I don't know. Is Lorenzo involved in your?
Not yet.
Not officially, but he is 2 doors from here. So
Yeah, so no, there was
definitely,
something
ask him to
interesting.
give a talk.
I remember there was quite something interesting, but I not really. I mean, I got comments on it. Was this? It's all different terminology, and you know.
Yeah, I think this might be related also to the story of celestial amplitude.
This celestial, yeah. Something. There was this word I remember.
Yeah.
But
Emilio is the expert above, and people in my energy,
I cannot say much more.
FPH are.
I've seen also Jan Molt. Wouter, do you remember seminars of Jan Molt speaking about?
Yeah,
celestial?
no, I mean, I think the part, I would say that the part where, so this is not my own expertise, but certainly when it came to understanding like energy correlators, I mean, you can write them in terms of light ray operators. And in fact, then you can also find the scaling behavior, like we would say in the QCD side, oh, we calculate some anomalous dimension and that gives you the scaling behavior, but you can also get this from the light ray OPE that also predicts then the scaling dimension. And so there's certainly examples where there was first results obtained from the light ray OPE, and then we also understood how to do it in QCD. So there's this example where you have like a 3-point correlator where you have two of the particles you're looking at are very close to each other. So it's something called the squeeze limits. And you can see some interference effects there. And that was first derived using the light ray OPE and then understood also like how you could do this in QCD.
Can you share the reference for it in the chat? Maybe.
Sure.
I mean, one idea for this network, if time by time we want to organize a Zoom seminar for all of us, even from people which are not inside our network. Magnier is one, Jan Molt can be another.
Yeah, we could have once a month, for example, a seminar once a month.
Once a month is, yeah, something like this.
Yeah, I agree. I mean, recently there has been a workshop at Simon Center about energy correlators, but I think it probably is the topic which is at the intersection, the most overlap between.
Probably yes.
Yeah.
In this moment, perhaps yes. At least this afternoon. Tomorrow,
Exact moments, yes.
I don't know if tomorrow afternoon I will think the same. But this afternoon perhaps seems to be.
Well, okay. I think for the complete success of the project, we should have some collaboration among different, from different work packages, but still a big, a solid, say, part of the proposal was to work within each work package. So, and
No. And for work package 2, I think, okay, me and Wouter collaborated since a long time. I think we'll continue. And I've seen also they're part of the Torino group of Elena, Oscar, and people like this. We and Andrea, we cross at every conference, but we have never worked together. So I don't know, probably can be an occasion to start doing. I have to say we have a kind of different philosophy about the same subject, which have prevented us to work together up to now. But I mean, we can try to find an agreement. And yeah.
So maybe I have a question from Volodya, which is I see him online. Can you hear me, Volodya? Nice. Yeah. So in the is there one of the example that you showed during the talk where the factorization theorems, where you can, using integrability, you can actually see the explicit result for the observable you were looking at, and also the statement from the factorization theorem. So I know, for example, there's some recent works by Smirnov, I think, where there's a particular quantity that is calculable in n = 4, which is the it's related to the it used to be related to the Caspar anomalous dimension, but you can compute it, and it's a different quantity. You call it the octagon anomalous dimension. So he asks himself that for the same quantity there are factorization theorems, but somehow this give you a parameterization of the function you're looking at that you know exactly, that is slightly more complicated than what it is in practice. So I was wondering if you have another example where you can see this phenomenon.
Well, this I don't know, but in principle, I think another field which is practically unexplored is that there are basically two sub-communities who are using conformal symmetry in a kind of different way. So there is this conformal symmetry which is in collinear processes, and this is this SL2R symmetry.
Yes.
And there is a Reggio community which is using SL2C symmetry, which is kind of another subgroup of the conformal group. But this is not a conformal group is not a product of these two subgroups. You cannot separate them. You either have one or you have other one. Yeah. But on the other hand, there should be some matching of results coming from the collinear region and from the Reggio region. So there should be some matching coming from this classification according to SL2C representation to something like comes from the Diglap region, if you wish.
I see.
And I think this is completely unexplored. So one particular problem that I, for example, have for some time, but I cannot say much about it, is that I demonstrated how we calculated these amplitudes, including power corrections in collinear region for all forward reactions. using this operator product expansion. But on the other hand, in the regular limit, there is old well-known result by Lipatov, how the BFQL solution looks for finite t.
Mhm.
In principle, they should somehow match each other.
I see.
But of course, this is different kind of expansion. But I don't know if you just have a conformal field theory. It should be, it should have both types of expansion. They should match somehow. Probably.
I see.
But this, I don't know. These kind of things are, I think, are completely unexplored. So,
I understand.
and they say I think there is a lot of the technical development possible because most of the conformal field theory methods are done for considering local operators. It is question not about ideology, but there is a lot of machinery. I mean, if you saying that you calculate something using conformal field theory method, it's just the same that you calculate something using perturbation theory. You have some methods, you have some bag of tricks how to do it. And this bag of tricks exists, it is very big, but it's more for correlation functions of local operators.
I see.
Extending it to some objects that we need would be quite useful, I think. It's a question of really machinery that could be useful.
I see. So
And as far as TMD studies are concerned, there is this result by, I think, Baletsky and Kirilli, that they observed that I think the leading order TMD evolution equations have some symmetry which looks like a reduced conformal symmetry in not in 3+1 but in 2+1 dimensional space, which would be natural because one dimension is separated. But it's just an observation. But how to use this, I don't know. They so far did not try to do anything with that.
I see. Thanks.
I don't know.
Maybe also in this case, if you have some reference, maybe you can give it to me later, or I will share it
I
afterwards.
don't have it in the moment, but I think if you just look at Baletsky plus Kirilli, since they don't write many papers, you will immediately find it.
I see.
It is.
And for the problem you mentioned at the beginning, the one where you want to match the Regge.
Well, there is no literature, I think. But I think the problem is there. But there is a different kind of classification that they should match. You know that, for example, if you have the usual BFQL, yes, if you just have usual BFQL, we know very well that it matches collinear factorization in some particular way. It corresponds to summations of some particular contributions in the collinear factorization. Yes, and so to leading order is quite simple.
But do you think yesterday we had a talk by Michelangelo, and I think he was showing us some matching of. Can that be related, or it's a?
No, this is sufficient. I am a little bit. Yeah, this I think there was similar work in the past. I think there was papers by Karachemsky, Manashov, Dergachev, and some guy with a Polish name, I forgot, who also did something like that. So I think it is known if you start with a BFQL solution, and then the normal dimensions lie on some complicated surfaces, Riemann surfaces, and it is known how they evolve. They evolve in a very non-trivial way. But my whole problem is actually with this kind of integrability is usually because it's about spectrum, and we need in our application we need the wave functions. I see. Also, okay. For example, in n equal to 4, there is this famous correspondence, right? There's correspondence, but this correspondence is at the level of anomalous dimensions. So anomalous dimensions of these long operators is related to something. Yes. But I don't know any language, correspondence language for the wave functions, because you have on a string side and a field series side, you would have some different randomization schemes. I don't know if you need to do it. And this is, I think, kind of pretty impossible to do. So we need in QCD also kind of the wave functions, not only the spectrum. In the things that we are using, of course, if you say that you're interested in the mass spectrum of hadrons, then of course you don't need that.
I see, I understand.
But objects that we need are usually scheme dependent. They are dependent on, and the scheme is in this message, I think, yeah.
Yes, yes. So the wave, just to clarify myself, the wave function, okay, of course, is also useful information, 3-point couplings of let's say the long operator and other operators, or of course if you have the wave function, you have...
So they know how these anomalous dimensions look like, yes?
Yes.
For the integer positive n, they know that they correspond to some local operators.
Yes.
At least in principle, for fixed n, that they can be found. You diagonalize the matrix, okay? But
Yes.
then, if you make an evolution along these complicated curves, then they could correspond to some probably some non-local operators.
I see.
Okay. They don't have any idea how to do it. Yes, and this is. I actually don't know how to solve a much simpler problem. If you wish, we very long ago we wrote a paper with Karchemsky and Manashov about randomization of 3-quark distribution amplitude. You have 3-quark operators, and not for n equal to 1, you have basically 1 operator. For n equal to 2, you have 2 operators, or something like that. When equal to 3, you have 3 operators. And then you want to put these anomalous dimensions on some curves. In leading twist, for each n, you have one anomalous dimension, and there is a thing that's called Carlson's theorem, right? That there is a unique function with some nice, with good behavior at infinity that goes through this integer points. If you have such a construction and the number of anomalous dimension increases with n, you don't know how to put them on the curves.
I see.
So naively, you could, for example, say, okay, let's put the lowest anomalous dimension on one curve, then second lowest on another curve, and so on, so on, so on. But you can start another way around. You can start from the top and put the highest on one curve next to highest, and so on. And basically, the statement is that it is both wrong.
I see.
It's both wrong, and if you go to if you start to go from integer n to non-integer n, they all mix in some very complicated way on these Riemann surfaces. Yeah. So this means for me that even if I have full results for the randomization of quark anti-quark gluon operators, I cannot write randomization group equations for quark anti-quark gluon correlation function.
I see.
Which is kind of yeah. It is just all, for example, leading order in alpha S. It is one loop result. So it's a well-defined object, in principle simple. But I don't know how to fix the analytic continuation.
I see, I understand.
Well, in the sense I know, but it is kind of complicated. I don't know how to do it. Yeah.
Vasco, do you think this is related to there was this paper by Alexandre and Pedro on the twist tree, where they find that the Regge trajectory there, it goes into the negative spin, but hits a lot of zeros?
Okay, so this I don't know. This I don't know this work. So, but yeah.
Yeah,
No,
I think it might be related to that. I'm not very familiar.
Just Vasco, just before you let me to the framework is the following. So you have a setup in which you have many operators, okay, but they have a threshold. So they start, for example, from dimension 3 and 4, Therefore, if you draw a Regge line, somehow let's say you are on a Regge line which starts where physical operator starts at dimension 4, let's say. But this line, of course, intersects also dimension 3, 2, etc. So you wonder what should happen with, for example, for 3-point function. That it means a 3-point function should have a 0 at the location of the should have a value at the location of physical operator, but should become 0 when you go to when you're on the Regge line, but the operator does not exist. In fact, they use a little bit this theorem that you mentioned of Carlson to get this kind of fit. So maybe Vasco, you have a comment on this.
Yeah, I just think that it might be related, but I should also study a bit better Pedro's paper that you talked about.
Yeah, so I think in that case, I think the analytic continuation that one is looking for is determined by requiring zeros in some, let's say, negative spin values or something like that. I don't know if this is useful related to your comment, Volodya, but it looks interesting.
What I know, which is probably true, is that analytic continuation is not such that, you know, one particular solution with fixed n goes to some other particular solution with full n. They are all mixed with each other.
I see. I see.
It is not, you know, you cannot just put them on simple trajectories. It's more complicated. And I think for the eigenvalues, it's kind of if you start from the range, I think these people started.
I see.
People started, I think, and this is possible. And you see how these anomalous dimensions of local operators arise. Also, I think this is kind of known, but what is not known are the wave functions. So this is how the wave functions evolve along this line. And this is complicated.
I understand.
I don't know because yeah.
But I guess that they study the wave functions, but yeah, I don't know exactly how.
I see.
But so will these wave functions be related to the wave functions of local operators? Just like in a simple way, it's just in some sense the analytic continuation of those. But those we usually think about as defined on a spin chain.
In median twist, if you start with local operators with fixed number of derivatives, the corresponding object is this light ray operator.
Mm-hmm.
Yes, and so you know it is a non-local operator, which is, but for twist no, for twist 3 already, I don't know how to do it.
Yeah.
No, of course it can be simpler. Okay, so it is certainly also some non-local object that should be also probably light ray like operators, but I don't know how to do it.
Yeah.
Thanks.
Yeah, like Jessica was saying,
in some sense, at least to really know that in Perturbation theory, solution must exist because I can forget. For example, let's take really the case of the simplest case will be just 3-quark operators. Yes, I can calculate the realization of this of the local operators, local 3-quark operators. I will have large matrices, so in principle I can diagonalize these matrices and find anomalous dimensions. You can do it. On the other hand, so in principle you don't need to do it like this. So you can simply use just standard perturbation theory already for the correlation functions, and then you will have kind of a D-Glab equation. It will be 2-dimensional. And this, in principle, gives you the whole evolution. So in principle, seems to be no problem. But if I start in the first way and I go first to the local operators, then I don't know how to go back. You see what I mean? It looks like, yeah.
I see.
it's not necessarily, I mean, it looks like a simple problem. It's not necessarily a very simple problem. It might be related because it is, if I write it in terms of the really perturbative, just perturbative calculations in one loop, then it is it will be two-dimensional evolution equation essentially. And then you can have, first of all, what are the boundary conditions that you use for the solutions? Then there could be some subsubtleties, there could be some singularities on the way, there could be some branch points in the solution. So I don't know. It might be actually not so. Yeah.
I see.
So these difficulties may be actually hidden somehow in these evolution equations in the momentum fraction space, which I can write in principle. But, so at first sight looks at a solvable problem.
Thanks a lot, Volodya. Are there any more comments or questions? Okay, if there are no more, maybe we can